Q6746-1, when density altitude is beyond capability as indicated on the performance chart? A. Interpolate the data and attempt takeoff. B. Extrapolate the data and attempt takeoff. C. Do not attempt takeoff until conditions permit calculations to provide the data to determine a safe takeoff and climb out. The correct answer is C. Do not attempt takeoff until conditions permit calculations to provide the data to determine a safe takeoff and climb out. Density altitude plays a crucial role in aircraft performance, particularly during takeoff. It is determined by considering factors such as temperature, pressure, altitude, and humidity. Density altitude values that exceed the capabilities specified on the performance chart indicate that the aircraft may face limitations and reduced performance. When density altitude exceeds the capability indicated on the performance chart, it is essential not to attempt takeoff until conditions allow for accurate calculations. In such situations, it is not advisable to rely on interpolation or extrapolation of data to estimate aircraft performance accurately. Interpolation involves estimating values within a range of known data points, while extrapolation involves estimating values beyond the range of known data points. Both methods are prone to increased uncertainty and may not provide reliable results, especially in critical situations such as takeoff with high-density altitude conditions. To ensure a safe takeoff and climb out, it is necessary to have accurate data and performance calculations specific to the current conditions, including density altitude. This typically requires waiting for conditions to improve or obtaining more precise measurements and information. By not attempting takeoff until conditions permit calculations, pilots prioritize safety and mitigate the risks associated with operating beyond the capabilities indicated on the performance chart. Waiting for suitable conditions allows for a thorough assessment of the aircraft's performance capabilities, ensuring a safe and successful flight. 6747. If the atmospheric pressure and temperature remain the same, how would an increase in humidity affect takeoff performance? A. Longer takeoff distance. The air is denser. B. Longer takeoff distance. The air is less dense. C. Shorter takeoff distance. The air is denser. The correct answer is B. Humidity refers to the moisture content in the air. When atmospheric pressure and temperature remain constant, an increase in humidity affects takeoff performance by making the air less dense. Humid air contains water vapor, which displaces some of the oxygen and other gases in the air. As a result, the air molecules are more spread out, reducing the overall density of the air. When the air is less dense, it provides less lift and reduces the performance of the aircraft during takeoff. With less dense air, the wings generate less lift, and the engine and propeller experience reduced efficiency. As a result, the aircraft requires a longer takeoff distance to accelerate and achieve the necessary lift for a successful takeoff. The reduced lift and efficiency caused by the less dense air due to increased humidity can affect the aircraft's ability to climb and perform other maneuvers as well. Pilots must consider these factors and make appropriate adjustments to their takeoff procedures, such as accounting for the longer distance required for takeoff and adjusting their speed and power settings accordingly. In summary, an increase in humidity, when atmospheric pressure and temperature remain the same, leads to longer takeoff distances because the air is less dense. The reduced density affects the aerodynamic performance of the aircraft, requiring more distance to achieve the necessary lift for takeoff. 6747-1. What is pressure altitude? A. The indicated altitude corrected for position and installation error. B. The altitude indicated when the barometric pressure scale is set to 29.92. C. The indicated altitude corrected for non-standard temperature and pressure. The correct answer is B. The altitude indicated when the barometric pressure scale is set to 29.92 inches of mercury, inHg. Pressure altitude is a standardized altitude reference used in aviation. It is defined as the altitude indicated when the barometric pressure scale on the altimeter is set to 29.92 in Hg, which is the standard pressure at sea level in the International Standard Atmosphere. The reason pressure altitude is referenced to 29.92 in Hg is to create a common reference point for all aircraft regardless of the local atmospheric conditions. By setting the altimeter to this standard pressure, pilots can compare altitudes accurately and consistently, regardless of variations in barometric pressure at different locations and altitudes. When the altimeter is set to 29.92 in Hg, it provides an indication of the aircraft's altitude above mean sea level, MSL, based on the standard atmospheric pressure at sea level. This allows pilots to determine their vertical position in relation to established altitude references and navigation aids. It's important to note that pressure altitude is not corrected for non-standard temperature or pressure variations. It serves as a reference for altitude comparisons and is used in performance calculations, such as determining aircraft performance at different altitudes, fuel consumption rates, and climb performance. In summary, pressure altitude is the altitude indicated on the altimeter when the barometric pressure scale is set to 29.92 in Hg. It provides a standardized reference for altitude comparisons and performance calculations in aviation. 6749. What effect does an uphill runway slope have upon takeoff performance? A. Decreases takeoff speed. B. Increases takeoff distance. C. Decreases takeoff distance. The correct answer is B. It increases takeoff distance. An uphill runway slope has a significant impact on takeoff performance. When an aircraft takes off on an uphill runway, several factors contribute to an increase in takeoff distance. Firstly, the uphill slope creates an upward incline that acts against the aircraft's forward motion. This results in a decrease in the effective component of thrust that contributes to acceleration. The available thrust must be used to overcome the uphill gradient, reducing the net acceleration of the aircraft. Secondly, the uphill slope increases the effective angle of climb required to clear obstacles or achieve a safe altitude. The steeper incline increases the aircraft's climb angle, which in turn increases drag. The increased drag further reduces the aircraft's acceleration and increases the takeoff distance required to achieve the desired climb performance. Additionally, the uphill slope affects the ground speed of the aircraft during takeoff. As the aircraft ascends the slope, its ground speed decreases compared to its indicated airspeed. This decrease in ground speed reduces the airflow over the wings, resulting in decreased lift production. To compensate for the reduced lift, the aircraft needs to maintain a higher indicated airspeed, which leads to a longer takeoff distance. In summary, an uphill runway slope increases the takeoff distance required for an aircraft. The uphill gradient decreases the effective thrust, increases the drag, and reduces the ground speed, all of which contribute to a longer takeoff roll. Pilots need to account for these factors and adjust their takeoff procedures and performance calculations accordingly when operating from an uphill runway. 6760. In a propeller-driven airplane, maximum range occurs at A. Minimum drag required. B. Minimum power required. C. Maximum lift/drag ratio. The correct answer is C. In a propeller-driven airplane, maximum range occurs at the point of maximum lift-to-drag ratio. The lift-to-drag ratio is a measure of the efficiency of an aircraft's wing in producing lift compared to the amount of drag it generates. To understand why maximum range occurs at the maximum lift-to-drag ratio, we need to consider the relationship between lift, drag, and power. In level flight, the total power required by the aircraft is the sum of the power required to overcome drag and the power required to produce lift. At minimum drag, the aircraft experiences low drag, but this does not necessarily lead to maximum range. It indicates a state of reduced resistance, but it may not correspond to the optimal balance between lift and drag for achieving maximum range. Similarly, at minimum power required, the focus is on minimizing the power needed to maintain level flight. While minimizing power can be beneficial in terms of fuel efficiency, it doesn't guarantee maximum range. Power requirements are influenced by various factors, such as airspeed and engine efficiency, which are not solely determined by the lift-to-drag ratio. On the other hand, maximum lift-to-drag ratio represents the point where the aircraft achieves the greatest lift force relative to the amount of drag it produces. This ratio directly affects the efficiency and performance of the aircraft. When flying at the maximum lift-to-drag ratio, the aircraft can cover the greatest horizontal distance, range, for a given amount of fuel consumed. Therefore, in a propeller-driven airplane, maximum range occurs at the point of maximum lift-to-drag ratio. This configuration allows the aircraft to achieve the most efficient use of fuel and travel the farthest distance per unit of fuel consumed.